In this presentation, I'm going to be going over polarity and how it relates to Vesper theory. Up top, we're going to do a review of Vesper theory. What are the shapes and how do we determine them? We'll then go over what is polarity. This is really talking about why molecules act sort of like magnets in some situations. We'll figure out how to determine polarity using both Vesper shapes and electronegativity. And finally, I'll show you how to use a software called MoleView that can help us see the polarity of an element or a molecule. So real quickly, let's go through a Vesper shapes review. Remember that Vesper theory allows us to convert two-dimensional Lewis dot structures into three-dimensional shapes of molecules. First, we would draw the Lewis dot structure. So let's say I have water, H2O. Once I create my Lewis dot structure, it should look something like in the top right. Next, we would make the AXE formula for the structure. In this case, one oxygen, A, connected to two hydrogen atoms, so X2. And the oxygen has two lone electron pairs, so that's our E2. And finally, we'd find the correct structure using our Vesper chart, or we go from memory. I'm going to bring up the Vesper chart on the next slide so we can use it to analyze this water. In this case, notice that we have the Vesper shape of AXE2. If we look at our chart, we can see that this is our bent shape up here. And that should make sense. We have four attached groups to the oxygen. Two of them are going to be electron pairs, and two of them are going to be just atoms. So we get this bent shape right here in the center. And we can see even this is our example, H2O. So this is our bent structure. Remember that we have five basic Vesper shapes if we don't count electron pairs. When two atoms are attached, we have a linear shape on the left. When three atoms are attached, we have a trigonal planar shape, the flat plane made of three atoms. When we have four groups attached, we have a tetrahedral shape. Five gives us trigonal bipyramidal, and six gives us octahedral. And remember, our somewhat more exotic shapes are when we replace, say, one of these groups on any of the structures with an electron pair. It doesn't change the overall shape, but because we've replaced one pair and we only have a few things remaining, the shape does end up changing, or our name ends up changing. So what is polarity? Well, polarity occurs because there's an electronegativity difference in the bonds of a molecule. We went through this in an earlier lesson. We said that elements with a higher electronegativity pull the electrons more towards themselves, and this causes polar regions in the molecule. Looking at this HBr over here on the right, if I look up on my electronegativity chart, the electronegativity of Br and H, we'll see the electronegativity of Br is 2.8, and we'll see the electronegativity of H is just 2.1. Going back a ways, we'll remember that our real idea about what's happening with these electrons in the bond are we have to talk about the difference in electronegativity. We know already that Br is going to be pulling these electrons more because it has a higher electronegativity, but we have to figure out what kind of bond we have. And to do that, we take the larger electronegativity and we subtract the smaller electronegativity. We would get a difference of 0.7, which, as we'll see on a chart later, that does give us a polar bond. Basically, what's going to happen is these electrons are going to move from the hydrogen and go more towards the bromine. And we use this kind of crossed arrow to show where the electrons are going. And it gives us a hint about charges. We can see that this positive region is going to be near the hydrogen because the electrons have sort of left it a little bit. And the electrons have sort of gone towards bromine, which gives it a partially negative charge. And we can actually represent that using this delta notation. We say delta negative to say the bromine is partially negative, and delta positive to say that the hydrogen is partially positive, because the electrons sort of left the hydrogen and sort of went to the bromine. So how do we determine polarity? Well, in three-dimensional molecules, the first case we would have is if we have a molecule that has all nonpolar covalent bonds and no electron pairs. This molecule would then be nonpolar. So first, let's get our electronegativity values for these hydrogens and this carbon. I'm going to bring up my electronegativity chart. Hydrogen has 2.1 and carbon has 2.5. So let's do this. If we find the electronegativity difference, hydrogen with 2.1 and carbon with 2.5, we actually a long time ago went through a chart where we said, what is the electronegativity difference? In this case, the difference between carbon and hydrogen is 0.4, and we classified that all the way over here on the right as being perfectly covalent. So there's no polarity here. There's no difference in electrons. Technically, the carbon is pulling a little bit harder, but it's so negligible or small that we say these bonds are nonpolar. So if I head back to my molecule, I can see that all four of these bonds are nonpolar. All of these bonds in red are going to be nonpolar. So this molecule overall has no polarity. There's no real region of especially positive or negative regions. So this is a nonpolar molecule. Because there's no separation of positive and negative regions. The electrons haven't moved closer to one atom versus another. Let's take a second example. If we have a molecule that has all polar bonds, but it is symmetric, the molecule is also going to be nonpolar. And let's see why. I'm going to head to my electronegativity chart. I see that fluorine has 4.0, carbon has 2.5. If I label these and get an electronegativity difference, we'll see each of these fluorines is 4.0 and carbon is 2.5. If I were to subtract these, I would see that my difference in electronegativity, if I subtracted 4 and 2.5, my difference would be 1.5, which would make these bonds polar. So in this case, I'm going to label these in blue, showing that each of these bonds is polar. And in fact, each of these bonds will have the same kind of behavior. The electrons are going to move from the carbon towards the fluorines, and that makes the fluorines feel a little bit negative, and it makes the carbon feel a little bit positive. So you would think that this molecule would be polar. We have negative regions and positive regions. This molecule would look like a magnet. The problem is that these fluorines are pulling equally and in opposite directions. Essentially, these two fluorine atoms at the top are going to be pulling oppositely in both directions. So there's overall no separation of charges in the top two. They also oppose the pull from the bottom two fluorines. There's no overall difference in the charge. So because these pull equally and oppositely, this molecule is going to be symmetric. And because it's symmetric, there is no overall polarity. So we'd say this molecule would be also nonpolar. Essentially, if a molecule has all of the same group attached in all directions, it's also going to be nonpolar because it will end up being symmetric. Our last case is when we have a molecule that has some polar covalent bonds and some nonpolar covalent bonds. We actually saw this we saw both of these bonds in our previous two examples. We saw the carbon to fluorine bonds were polar, and so the electrons moved towards the fluorine. And we saw that the hydrogen-carbon bonds were nonpolar. So there's really no difference in charge. Because we have these fluorines pulling these electrons farther from the carbon, they both end up feeling negative. The carbon ends up feeling positive. And now we have this difference across the molecule. If I look at my molecule over here, I would end up thinking that there's going to be some kind of a negative region down over here. And there's probably going to be some kind of a positive region to oppose it on the other side of the molecule. Because there are polar covalent bonds and the molecule is asymmetric, this is going to end up also being a polar molecule. The last case is very similar to what we have before. Know that lone electron pairs count as a different, very negative group. So in this molecule, believe it or not, oops, daisy, in this molecule, nitrogen to chlorine, these bonds are all perfectly nonpolar. Nitrogen and chlorine have the same electronegativity. Offhand, I believe they are both 3.0. So there's no separation of charge. However, this lone electron pair up top, these are electrons that aren't bound to anything. So they feel especially negative. Therefore, this molecule, even though these three bonds are nonpolar, there's still this large negative region up top. So because there's this asymmetry, these kind of molecules also end up being polar because they're asymmetric and there is this large region at the lone electron pair that is polar. Really quickly, let's go through MolView. This is a software that can help you see polarity. This is going to be the older version of MolView, which is in our current folder. Let's say I wanted to make a molecule. I'm going to make one of the ones we saw in the examples. We'll do C, F2, H2. The way this software works is first you're going to want to select these two options up here, the color version, and then this C to H. That's going to show us all the atoms. And then I'm going to go through this one more time to create our molecule. You will click on the right side to select an atom, click to place. I'll zoom in by kind of scrolling forward. And now I want to place two hydrogens and two fluorines around the outside. To do that, I'll click on hydrogen. I'll click this single bond in the top left, and then I will click and drag away from the carbon. Notice it defaulted back to carbon, so I'll reselect hydrogen and click to change these. I'll now add on two fluorines. And now I've created my Lewis dot structure. Now the way this software works is on the right side, it shows you the molecule. This is still the old molecule. To update it to the new one, I'm going to click this 2D to 3D button. It'll show me my molecule. I'll scroll to zoom in. You can probably pinch to zoom as well. And if I orient this the same way as I have in my structure, by clicking and dragging, let's see if I can get it. There we go. That looks similar to what I have on my Lewis dot structure. I can actually use a function to see the polarity. This function's a little bit hidden. You have to go into this JMol up here and click this MEP, surface lucent. And I'll ignore this for a second. When it pops up, you'll see that there's this separation of charges. You get these very negative regions in red around the fluorines, and you get these very positive regions in blue around the hydrogens. And this can show us visually that we have this magnet of a molecule. We have this this polar molecule. When you see these differences in charges, it can confirm that this molecule is polar. I hope this tool, as well as the presentation, helps you understand polarity a little bit better.